There's a phrase that gets repeated inside Boeing's strategy meetings, almost like an inside joke everyone quietly believes without ever questioning it. China is always 10 years behind. Say it enough times, and it starts to feel less like an opinion and more like a law of physics. But in 2026, that comfortable assumption got shaken in a way almost nobody in the industry saw coming. And the reason has almost nothing to do with what most people assume. It didn't happen because the C929 suddenly took its first flight. It hasn't flown. It didn't happen because China unveiled a finished certified engine ready to power a wide-body jet across oceans. That milestone still hasn't been reached either. Instead, the shock came from something quieter, buried inside a test stand result and a regulatory handshake that most casual aviation followers scrolled straight past without a second thought. Put those two pieces together, though, and you start to understand exactly why engineers at Rolls-Royce, GE, and CFM are reportedly paying very close attention right now. So what actually happened? Why is China's homegrown engine program suddenly the center of so much quiet conversation inside the aviation world? And why should you care, even if you've never thought twice about what's bolted underneath an airplane's wing? Stick around, because to really understand why this engine story matters, we need to rewind the clock first, because the full picture only makes sense once you see where this entire program came from. Picture aircraft certification like the most brutal driving test imaginable. Except instead of one examiner sitting beside you with a clipboard, you need dozens of them, pulled from multiple regulatory agencies, each one obsessively picking apart a different piece of the aircraft. Every wire gets traced, every bolt gets torque tested, every single line of flight control software gets scrutinized character by character, because if any of it fails at 35,000 feet, there's no pulling over to the side of the road to sort it out. And nowhere is that scrutiny more intense, more unforgiving, than when it comes to the engine itself. An airframe with a flaw might still glide. An engine with a flaw simply fails, and failure at altitude is not a category aviation regulators tolerate under any circumstances. That's exactly why the engine question, sitting at the heart of China's wide-body ambitions, carries so much weight, arguably more weight, than almost any other single decision in the entire program. Now, here's something a lot of people forget. This particular Chinese wide-body jet, the C929, wasn't originally a solo Chinese effort at all. It began life under a completely different name, the CR9-29, built on a 50-50 partnership between China's state aviation giant COMAC and Russia's aircraft maker UAC. Two nations with very different aviation histories agreed to split both the enormous cost and the enormous engineering risk of building a wide-body jet completely from scratch. On paper, it made a strange kind of sense. Russia brought decades of experience building large aircraft dating back to the Soviet era, along with genuine expertise in large-scale jet engine design. China brought capital, manufacturing scale, and a domestic market big enough to make the entire venture commercially viable on its own. Together, the idea was to build a jet capable of taking on Boeing and Airbus without either country having to shoulder the full burden alone, engine included. Then the geopolitical landscape shifted. International sanctions hit Russia hard, and almost overnight, UAC's access to Western financing, Western components, and Western technology collapsed. Suppliers pulled out. Banks froze credit lines. The infrastructure a modern aircraft program depends on, global supply chains, international insurance, cross-border financing, simply stopped being available to Moscow. And quietly, without a dramatic press conference, without any public finger-pointing, Russia walked away from the partnership entirely. No more 50-50 split, no more shared engineering risk, and critically, no more shared engine expertise either. China faced a genuine fork in the road at that moment. It could cancel the entire program, absorb the sunk costs, and let the whole idea quietly fade away, the same way plenty of ambitious aviation projects around the world have faded before. Or it could shoulder the entire weight of the project alone, engine development included, a task that suddenly looked far more daunting without a partner who actually had prior experience building large-scale jet turbines. China chose to shoulder it. The aircraft was renamed, becoming the C929 we discussed today, and every unresolved technical problem, every dollar of financial risk that Russia would have shared, became China's burden to carry by itself. And that burden fell hardest on exactly the part of the aircraft most people never think about, the engine bolted underneath each wing. Then, in 2026, something shifted on the regulatory side that most casual aviation fans completely missed, even though it sets the stage for everything happening with the engine program today. China's aviation regulator, the CAAC, sat down with aviation authorities from Hong Kong and from Macau, and the three of them signed something called a cooperation arrangement. Say that phrase out loud, and it sounds like exactly the kind of thing that gets filed away in a government archive and forgotten. It sounds like bureaucratic housekeeping, the sort of paperwork nobody outside a regulatory office would ever bother reading closely. It is not that at all. For the very first time in the program's history, Beijing is inviting outside certification specialists directly into the process of approving its newest, most ambitious, most expensive aircraft yet, a genuine wide-body built specifically to go head-to-head with the Boeing 787 and the Airbus A350 on long-haul international routes. And here's why that detail actually connects directly back to the engine story. No matter how impressive a domestically built engine eventually becomes on a test stand, it still has to pass through exactly this kind of international credibility gauntlet before airlines outside China will ever trust it, hanging beneath a jet full of passengers. So why Hong Kong specifically, out of every possible partner China could have chosen? The answer comes down to credibility, and credibility is really the connective tissue running through this entire story. Hong Kong's aviation authority already operates much closer to international norms than mainland China's regulatory system does on its own. It follows a framework that lines up closely with the same standards used by European regulators and American regulators, the very organizations whose stamp of approval determines whether an aircraft, and everything bolted onto it, can legally fly into major international airports. By training alongside Hong Kong's certification specialists, China isn't simply trying to build a plane faster. It's rehearsing, quite literally. Practicing for the moment when the rest of the world has to decide whether it trusts a safety certificate stamped in Beijing, engine and all. Because here's the uncomfortable truth nobody in the industry says out loud very often. An engine can produce a spectacular thrust number in a controlled test environment and still get effectively locked out of global markets if the right regulators refuse to sign off on it. In other words, this cooperation arrangement isn't really about paperwork at all. It's about credibility, and credibility happens to be the one thing that money simply cannot buy in aviation, no matter how impressive the raw engineering numbers look. So let's talk about where the overall C929 program actually stands right now, because context matters before we go deep into the engine itself. Here's what's actually confirmed as of today. Preliminary wind tunnel testing is underway, the first genuine physical proof that the aircraft's shape can slice through the air the way engineers designed it to on paper. Alongside that, CAS officials are already sitting inside COMAC's design review meetings, weighing in on choices while the aircraft is still being sketched out, not after the design has already been locked in and frozen. That kind of early regulatory involvement has genuinely never happened this soon in any previous Chinese aircraft program. On the commercial side, Air China has put its name down as the aircraft's launch customer, signing a preliminary agreement at the Zhuhai Air Show, China's marquee event for showcasing its aviation ambitions to the world. But here's where we need to be completely honest with you, because a channel that only tells you the exciting parts isn't doing its job. COMAC's own leadership, speaking publicly at the 2025 Paris Air Show, put the target for a type certificate at 2032, with the aircraft not expected to carry its first paying passenger until 2035. Read those numbers again. That is not next year. That is not even within the next 5 years. And here's the part that matters most for our engine story today. None of those timelines can possibly hold if the engine itself isn't ready in time, which is exactly why what's happening inside China's engine test facilities right now deserves so much more attention than it's currently getting. Now let's talk about the actual scope of what China is attempting here, because once you see the full picture, the engine challenge becomes even more staggering by comparison. The baseline version, known as the C929-600, is being designed to carry 280 passengers with a range of roughly 12,000 kilometers, far enough to connect almost any two major cities on the entire planet without needing to stop for fuel. That figure puts this aircraft on a direct collision course with the Boeing 787, the Airbus A330neo, and the Airbus A350. Every one of those competing aircraft flies on a mature, extensively proven Western engine with millions of accumulated flight hours behind it. That's the bar China's homegrown alternative ultimately has to clear, not just on a test stand, but in daily commercial service, year after year, flight after flight. On materials, COMAC is targeting roughly 50% composite materials and around 15% titanium across the airframe, concentrated specifically in the areas that experience the most mechanical stress, places like the engine mounts and the landing gear structures. To really appreciate how enormous a leap that represents, consider that China's earlier regional jet program used just 1.5% composite material in its construction. Jumping from that number to 50% is roughly equivalent to a factory that has only ever assembled bicycles suddenly attempting to build a Formula One race car. And notice something important there. The engine mounts sit right at the center of that materials challenge, meaning the airframe and the engine program aren't developing in isolation from each other. Every delay or design change on one side ripples straight into the other. And then, finally, Let's talk about the money, because the financial story here tells you almost as much as the engineering story does. In late 2024, 8 separate state-owned shareholders poured a combined total of roughly $6.2 billion into COMAC, very nearly doubling the company's available capital in a single move. Think about what that kind of investment signals. In most publicly traded companies operating under normal market pressures, a full decade of delays and missed targets would trigger genuine panic among investors, possibly even outright cancellation of the program to cut further losses. Here, in COMAC's case, a decade of delays simply triggers another round of funding, another injection of state capital, another vote of confidence from Beijing. That's both the quiet advantage and the quiet danger baked into a program that's fundamentally built on political will rather than pure market demand. And nowhere is that funding advantage more relevant than in engine development, historically one of the most expensive, most failure-prone parts of any aircraft program on Earth. Now, let's get into the engine story itself, because this is genuinely where the ambition runs headfirst into reality, and it deserves a much closer look. A Western engine option, something from Rolls-Royce or from GE, remains technically possible on paper. These companies have decades of proven experience building reliable wide-body engines that airlines around the world already trust without a second thought. But that option is politically fragile under current export restrictions. And fragile is putting it kindly. A single shift in the geopolitical climate could take that option off the table entirely, and COMAC knows it better than anyone. So, in parallel, China is racing to build its own homegrown alternative, developed by the domestic engine maker AECC. In January of 2026, that engine hit 35.2 tons of thrust on a test stand, a figure that puts it in the same general weight class as established engines like the GE9X. On the surface, that's a genuinely impressive engineering achievement, exactly the kind of number that grabs headlines and understandably shocked plenty of people following the aviation world closely. It deserves to be recognized as real progress, not dismissed. But here's the catch that almost nobody likes to talk about openly, and it's the part of this story that matters more than the headline number itself. Producing a strong thrust figure in a tightly controlled test cell environment is a completely different challenge from having an engine that's fully certified, mass-produced at scale, and trusted by airlines to run reliably for millions of cumulative flight hours without unexpected failure. That gap between an impressive test result and a proven, dependable production engine has swallowed entire national aviation programs before in more than one country, and it tends to happen quietly without dramatic headlines, just years of delay stacking up one after another. In commercial aviation, an unresolved engine decision can silently push back an entire aircraft program by an entire decade, because everything else, the wing design, the fuel systems, the weight distribution, ultimately has to be finalized around whichever engine actually gets selected. There's also a quieter dimension to this engine race worth understanding, because it isn't purely a technical race, it's also a workforce and supply chain race. Building a reliable wide-body engine doesn't just require a design team capable of drafting impressive blueprints and hitting an eye-catching thrust number once on a test stand. It requires an entire ecosystem of specialized metallurgists capable of working with exotic heat-resistant alloys, precision machining facilities capable of manufacturing turbine blades to tolerances measured in fractions of a millimeter, and quality assurance pipelines refined over literally millions of hours of accumulated real-world flight data. Rolls-Royce and GE didn't build their reputations overnight. They built them across decades of iteration, including plenty of expensive early failures that never made it into glossy corporate history pages, engines that cracked under stress testing, blades that failed at temperatures nobody had modeled correctly, years of trial and error that simply had to happen before reliability could be trusted at scale. AECC is attempting to compress that same learning curve into a fraction of the time, backed by state resources that Western engine makers, even SAR, had access to in their own early years. That resource advantage is real, and it shouldn't be dismissed, but resources alone have never been enough to skip the fundamental physics of engine reliability testing, and that's precisely why so many industry analysts remain cautiously skeptical about firm certification timelines, even as they acknowledge the genuine progress behind that 35.2-ton thrust figure that shocked so many people when it was announced. Look at China's own C919 program if you want physical proof of exactly how long this kind of gap can stretch. And notably, that aircraft actually flies on a Western engine option today, which makes the comparison even more telling. The C919 was certified domestically back in 2022, a genuine milestone at the time, and yet 4 years later, it still doesn't have approval from Europe's aviation regulator or from America's FAA, the two certifications that would allow it to fly commercial routes into most of the world's wealthiest aviation markets. European officials have suggested that approval could realistically stretch out until 2028, possibly even as late as 2031. That's not a minor bureaucratic delay. That's nearly a full decade. between domestic certification and genuine international market access. And that's with an aircraft flying on an engine option. Western regulators already understand intimately. Now imagine that same certification gauntlet applied to a completely new, fully domestic engine that international regulators have never evaluated before. COMAC's broader delivery record hasn't done much to bolster confidence either. In 2025, the company delivered 41 aircraft across its entire combined lineup, a number that fell well below what it had originally promised to airline customers and investors. So yes, the engine news out of China's test stands is real, and it's genuinely significant. Significant enough to explain why this story has generated so much buzz across the aviation world. But it represents one bright spot along a much longer, much harder climb than most headlines make it sound, and understanding that distinction is exactly what separates informed excitement from blind hype. It also helps to compare this moment to how other emerging engine programs around the world have played out, because China isn't the first country to try leaping straight from an impressive test bench result into a fully trusted production engine. Japan's own attempt at building a homegrown regional jet engine ran into years of unexpected reliability issues that never showed up until the engine had already logged serious testing hours, forcing repeated redesigns long after the program's original headlines had faded from public memory. Even well-established Western manufacturers have had engines that looked flawless in early testing, only to develop unexpected issues once they accumulated real-world flight hours across different climates, altitudes, and maintenance conditions, issues that sometimes only appeared after years of commercial service. That's not a criticism aimed specifically at China's program. It's simply how jet engines work everywhere in the world, and it's exactly why regulators build in years of scrutiny before granting certification, no matter how good a single test stand number looks. A 35.2-ton thrust reading is a snapshot in time. Certification is a marathon built on thousands of those snapshots, repeated under every imaginable condition over years, not months. There's another angle worth considering too, the sheer scale of the industrial base needed to eventually mass-produce an engine like this, assuming it clears every certification hurdle. A single wide-body jet needs 2 engines, and an airline ordering dozens of aircraft needs a reliable pipeline capable of producing spare engines, replacement parts, and maintenance support for decades after the original sale. Rolls-Royce and GE have spent generations building exactly that kind of global maintenance and parts network, with service centers and trained technicians positioned across nearly every continent. AECC doesn't have that infrastructure yet, and building it isn't simply a matter of money, though the state backing certainly helps. It's a matter of time, trust, and thousands of accumulated real-world data points that simply can't be rushed, no matter how much capital gets thrown at the problem. That's the less glamorous, less headline-friendly side of this engine story, the side that rarely gets mentioned in the excitement following a strong test stand result. And now here comes the twist, the part of this story that might genuinely change how you look at everything we've just covered, because it turns out the engine race isn't the only place where China's supposed self-sufficiency story gets complicated. COMAC recently signed a letter of intent with a company called Aviation to build the C929's core avionics, essentially the electronic brain that runs the cockpit display. Eyes, the flight control systems, every digital process that keeps this aircraft thinking and responding in real time, including the systems that will ultimately monitor and manage whichever engine ends up powering it. And here's the surprise buried inside that announcement. Aviation is not a purely Chinese company at all. It's a 50-50 joint venture. One half belongs to Avic, China's state-owned aviation manufacturing giant. The other half belongs to General Electric, an American company headquartered thousands of miles away in the United States, a company that, notably, also happens to build some of the very wide-body engines China is trying to replace with its own homegrown alternative. So sit with that for a second, because the irony here is almost poetic. This is the aircraft that was born directly out of Russia's exit from the original partnership. This is the aircraft China deliberately chose to carry alone, rather than risk depending on another foreign partner ever again. This is the program explicitly designed, at least in the public narrative, to prove that Beijing no longer needs the West for its most advanced aviation technology, engines included. And yet, sitting quietly at the very center of that aircraft's cockpit, inside the systems that will ultimately keep it flying safely and managing whatever engine gets bolted underneath its wings, there are the fingerprints of an American company. So, which version of this story is actually true? Is China's engine program genuinely on track to deliver full independence from Western propulsion technology, the way the exciting test stand headlines want you to believe? Or is it something more nuanced, China simply becoming far more selective and strategic about exactly which pieces of Western technology it's willing to keep, depending on while it builds out everything else, Personally, I think the honest answer sits somewhere in between those two extremes, and the engine story is probably the clearest example of that tension in the entire program. But I want to hear what you think. Drop your take in the comments below, because this is exactly the kind of debate this channel exists for. If a plane built specifically to prove China doesn't need the West anymore, still needs American technology just to think and process information, how much of the independent engine narrative is actually real? And how much of it is careful public relations layered over a much messier, more interdependent reality? That question gets even sharper the moment you zoom out and look at the broader engine race happening across the industry right now, because China isn't the only country chasing this exact same dream of true propulsion self-sufficiency. Russia has been pursuing its own homegrown alternative for years now, an engine developed specifically to power large wide-body aircraft without relying on any Western supplier whatsoever. So here's the question worth asking. Who is actually closer to achieving a truly independent, fully domestic wide-body engine right now? Is it China, the country that just lost its original Russian partner and is racing to fill that gap with a brand new engine program built almost from scratch? Or is it Russia itself, the country that has spent decades building large aircraft engines but is now operating under some of the harshest technology restrictions in the world? That comparison, China versus Russia in the race for genuine engine independence, is exactly the story we're breaking down next. Before we get there, if you've made it this far, take a second to hit that subscribe button, because we cover stories exactly like this one every single day. From Boeing and Airbus to Comac and every other player quietly reshaping the future of commercial aviation. And to everyone already subscribed, genuinely, thank you for being part of this community and following along with these deep dives week after week. Your support is the reason we can keep digging into stories like this one instead of just repeating the same press release headlines everyone else in this space recycles. So here's where that leaves us. China's engine program just delivered a test stand number that shocked plenty of people paying attention to the aviation world, a genuinely impressive milestone that arrived alongside a quiet regulatory move most casual observers completely missed. Neither one, on its own, changes everything overnight. But together, they tell you something important about how seriously China is approaching the single hardest, most failure-prone part of building a competitive wide-body jet, the engine hanging beneath each wing. Boeing and Airbus certainly seem to think so, because behind closed doors, both companies are reportedly watching this development far more closely than either of them would ever publicly admit. The question now isn't whether China can eventually produce an engine capable of hitting impressive numbers on a test stand. The real question is whether that engine can survive millions of flight hours, earned certification from regulators who've never trusted a Chinese power plant before, and convince airlines outside China to bet passenger safety on it, and that answer is still being written, one test stand result at a time. The video breaking down the Russia comparison is coming right up next, so make sure you don't miss it. Subscribe now, and I'll see you in the next one.